Hello and welcome to this video lecture. In this video we will be talking about uninformed search, and in particular we'll be talking about breadth first search. So let's start. So breadth first search is part of a search algorithm that is called an uninformed search. What is uninformed search? Uninformed search is a search algorithm which attempts to find a goal, some sort of goal G, and it has no information whatsoever about where that goal might lie. So it is completely blind and it wants to explore and find where can I find G, but it has no information where G is. An example of this is if I leave you in a city at an intersection where you do not know anything about that city, and there is no people in the city also, so hypothetically speaking, there is nobody that you can talk to and get information from, and I tell you, well, you have to go to a shop X, and that shop is like 10 blocks away from you, and you look at the intersection, there are like 5 or 6 roads. Let's take the example of 6. There are 6 roads in this intersection going in different directions, and I just leave you there and leave, and now you have to find your way to the shop that I want you to go to, and you need a methodology or certain steps in where you can actually find the shop. Okay, so this is basically a search problem, a typical search problem where you're trying to find something and you have no information whatsoever. You don't know anything about the city, you don't know where the north is, where the south is. There is no information that you have, and you want to do the search and find this shop. So this is called an uninformed search, and breadth first search is one of the algorithms that help you in finding these the goal. If you don't have any information but you have some sort of idea of what, or you can actually explore things one at a time. So one of the things you might do is you are standing at this intersection, and then you select one of the roads, and you go 1 block away and see if the shop that I want is there or not, and then what you could do is come back to the same point that you were in if you didn't find the shop, and then try another road, and then the 3rd road, the 4th road, the 5th road, and the 6th road, until you exhaust all the roads that are on that intersection. And if you don't find the goal, then you try going a bit deeper, and you go to 2 intersections, and then you go back to the 1st road, and you go to the 2nd intersection, and if you don't find it, come back, go to the 2nd road, go to the 2nd intersection. And as you can see, we are expanding slowly. In this example, if you are thinking of it in a radial fashion, so we are increasing the radius from 1 block to 2 block to 3 block to 4 block until we find our goal. Okay, so this is one method of doing search, and this method is basically called the breadth first search. Okay, so the breadth first search is an uninformed search, and it's basically a simple strategy there where the node that we start from, or the location that we start from searching, is called the root node, and what we do is we explore all possible path from this root node. Okay, so you might get a graph, and you can represent your problem in a graph, whatever the problem is, and then try to construct a tree out of that graph. And for example, let's suppose that this is the tree that's on the right hand side over here, is shown onto my screen over here, and this is a tree. So we are starting at node S, and we would like to reach a goal that is labeled as G. So this is basically our goal. So this is a goal, and as you can see, there are multiple ways of going to the goal. Okay, and this is the tree of our problem. Okay, so this is basically the search space in which I'm going to do this the search on. But remember, breadth first search is an uninformed search. So when you start the search, this tree is not given to you, okay? Or you do not know what the tree looks like. But this tree over here, we're putting it as an example so that makes life easy for us in explaining. And what we want is some certain steps in which we follow so that we can be absolutely sure that we'll find a path between the source and the goal that we are looking for, okay? So in the breadth first search, the algorithm uses or explores all the successors first, and then determines whether it reached the goal or not. If not, then it goes from the successors and tries to do that. So what does that mean is we start from S and then we start exploring A and then we B, and we see that neither A nor B is the goal. So we go to the children of A and B, which are B and D, or the successors of A, which are B and D, and successor of B are A and C, and we explore these and see if we reached the goal. If we did not, we go to the successors of these and we try to find the goal, and sure enough, in that level we will find that we have reached the goal. However, as you can see, the breadth first search goes level by level in doing the search. Okay, so this is basically the main idea of breadth first search, and we'll dive deep in detail and we'll get you an algorithm that can actually do that, you'll see how the computer or an intelligent agent would take steps if it wants to use a breadth first search to go from a source node to a goal node. Okay, so here's the explanation again. So we start from S, and from S, like the intersection that you're standing on, you explore the first road and the second road. So you go to A and B and you find that you did not reach the goal, so you decide to go a level deeper. So you go from level 1 to level 2. So you explore from A, B, and D, and you explore from B, A, and C, and you keep on exploring until you reach to the goal. And in the next level, you will find that you reach to the goal. Okay, so this is basically the way that the breadth first search conceptually works. Okay, so the breadth first search can be implemented using something called a queue. So we talked about the queue in previous lectures, and what we will do is we will utilize this queue to implement the breadth first search, because it makes our lives much more easier. And we want to note over here that the front of the queue is called the head. It is the element that is going to be served, and the algorithm checks all paths at a given length. Okay, so that's what the algorithm should do. And for the algorithm, there are 3 inputs that it takes. It takes a graph. So whatever the problem is, you have to turn it into a graph and give it to the problem, and the problem then can actually work on it. And then you have to give it which node you want to start from and which node you want to end at. In this particular example, it is starting from S going to G, but in real life it could be from A to B, from A to Z, from W to C, whatever node that you want to go from and reach to. Okay, so the goal is where you want to reach to, and S is where you start from. Okay, and the goal of this algorithm is to return a success. So if the goal exists in the tree of the problem, then it should return a success. If the goal is not in the tree of the problem, then it should return a failure, and it should say that I was not capable of finding the goal that you want, because it's not within the tree that that you have given me, or the graph that you have given me. Okay, so let's look at take a deep dive into the details on how are we going to do this. Okay, so let's start with this algorithm. So there are 2 things that are shown over here. One on the left, which is an algorithm that's written, and on the right, what we have shown is a graphical representation of the same algorithm. Okay, so whether you look at the left or on the right, they're the same thing. One is written in an algorithmic way. The one on the right is written on a graphical way, a flowchart of way, where it's sometimes easier for some people to follow the flowchart, whereas other people would like to follow the algorithm over here. Before we start the algorithm and see how it actually works, I'd like to bring your attention to 2 counters that we are putting over here. This is the extended node counter and an enqueued node counter, and this is basically to count how many times have we actually extended something and how many times we enqueued something. So enqueued means how many times we have put something into the queue. So if you put an element into the queue, you have to increase the enqueued node by 1. And if you extend the node, so if you take a node and generate its children or the successors of this node, then you need to add this by 1. Okay, so there are 2 counters that we have. Okay, so we'll start in this algorithm and we will set the queue to have the element S. Okay, so this is let's go over here. It's visual, it's sometimes more clear for people to understand. So we initialize the queue with S. Since we initialize the queue with S, the number of enqueued node that we start with should be 1, and the number of extended node, because I did not generate the children of any of these nodes, they should be set to 0. Okay, so that is why the enqueued node is 1 and the extended node is set to 0. The enqueued node is equal to 1 because we have enqueued S into the queue. So we have put S into the queue, and that is why it is set to 1. Okay, so this is what's happening. Let's initialize the queue with the root node, and then what we do is we check if the queue is empty. Of course, the queue is not empty because we just added S, the root, into it, where we want to start the search from. So it will go to the no part. It will not go to the yes, because if the queue is empty, we just stop. But the queue is not empty. What I do is I extract the head and I check if the head is the goal. Okay, if the head is the goal, I have reached my goal, and that's it. I should go and return a success and stop. Okay, but for most examples, when you start searching, that might not be true, so you might not be at the goal node. So what we'll do is this condition will go to the no, and then in the no, now we want to generate the children of the head. So now you generate the children of the head. In the example of the intersection, then you start with the node that you are, with the intersection that you're in, and then for each one, you need to, for each road connecting to this intersection, you need to label the other intersection by a certain label, and then get to know these things. And then what you need to do is, after you generate the children, notice when we generate the children, we have extended the node counter. We are going to add to it 1 because we have extended this node. So what we will do is we will add the extended node counter by 1, stating to the algorithm that there is 1 node that has been extended until now. Okay, and then what we will do, we'll delete the head and we will append the children to the queue. So the same queue that we took the head from, which had the root that we started from, we're going to append the children into that queue. But in appending, please observe that you have to append in lexical order. And lexical order means that if you have multiple nodes A, B, C, D, the one that has A is going to go first, then B is going to go second, C is going to go third, D is going to go fourth. Okay, so it's not going to be D, then C, and B. No, it's lexically ordered. So please follow the lexical order, and we'll have an example on how we can do the lexical order in appending into a queue when we take the example. So we append the generated children, and when we append the generated children, notice we put something into the queue, and that's why we have to increase the number of enqueued nodes. So how many nodes are we adding to the queue? We increase it by the number of children's added. So how many children are we going to add? The enqueued nodes will be incremented by the same amount, so that we can count how many people or how many children have been added into the queue. And then we get back over here and we check if the queue is empty or not. If it's not empty, we repeat this until we find the head, and when we find the head, we return a success. Okay, and if the queue gets empty, then we declare the failure and we end. We don't return a success. That basically means returning a failure. Okay, so this is a graphical notation, as I told you, and the same thing is written over here. So it's a bit more in detail. So delete queue.head. So you're taking the head and deleting it. This number 8 over here is the same as this instruction, delete head over here, and the same algorithm is going in both representation. Whichever representation you like, you can choose and try to work with those representations. Now let's take an example and see how does this algorithm actually work. Okay, so here's an example. So let's suppose that this is the tree that we have, and I forgot to mention one thing over here, that the breadth first search does not take in consideration the weights of the edges. Okay, it ignores the weight of the edges, and it finds a route between S and G without looking at the weights of the edges. Okay, so whatever the weights, it doesn't care. What it wants to do is to find a path between the source and the goal, and if it can find one, then that's it. It doesn't care how efficient that path is. Is it the least cost path? Is it the most cost path? It doesn't care about that. The breadth first search doesn't take care of the weights. There are other algorithms that we're going to talk about that will do that, but for now, for the breadth first search, no weights are there. Okay, so when we start this algorithm, notice at the start we say initialize the queue with the root, and we are starting from S, so we initialize our queue with S. Notice the S that is over here. Okay, so we have an S over here, and what we want to do is let me take a laser pointer, and what we want to do is we go from the S, and then we extract the S, we take it out, and then after that in the algorithm that we had, okay, if I just go back, okay, why is this? Yeah, so if I just go back in my slide, after I do the initialize the root with the node, the queue with the root, I check if it's empty, I extract the head, and I then if the head is not the goal, I generate the children. So I extracted my head, okay, and I generate the children. The children of S is A and B, okay, and so S will have two children, A and B, and then I append them into the queue, and when I append them into queue, I observe the lexical order, and in the lexical order, A goes before B, and hence we add SA first and SB the second element in the queue. So the first element, or the head, becomes the SA, and the SB is the tail of the queue now. Okay, so the head is always the one that's on the left, and the tail is the last element in the queue. Okay, so the head of the queue becomes SA and SB, so, and we delete the head, and then what we do is we take SA, take it out. When we take SA out, the SB is going to go to the head, and then we generate the children of SA. Now notice the children of SA is SAB and SAD. What we do is we append the children, and the appending will be happening at the end because this is a queue, and the queue, notice SAB is going to be there and SBC is going to be there, and of course when we're inserting we observe the lexical order again. A goes before C. Okay, so whatever is in the queue we don't touch, but whenever we append, it has to be in the lexical order. Okay, so whatever we append is going to be inserted in a lexical order. Then we go again, we take the SAB, this is the head, we extract it. So SAD, SAB, SBC will remain the same. So they will move forward in the queue, and SAD will become the head. And then SAB, notice SAB, and I want to generate the child of SAB, so it's SABC. Okay, so I go ahead and append that SABC. That is the only child that's over there. Okay, so that's what's going on over here. And then we take the SAD, and when we extract it, we'll have the remaining elements copied over here, and then the SADG is going to come. So SADG, this is the element that is going to come to the end of the queue. And then we're going to take SAB, SBA, so this is the root SBA, and the SBA generates for me a SBAD, and that's going to be deleted from the head, and I'm going to add this element into the queue. Okay, and then we're going to take the SBC and generate the child of the SBC, so the SBCE is going to be generated and appended at the end. Okay, and then we are going to take the SABC and then expand that, so SABC will have SABCE appended at the end, and I reach to the SADG, and since now my goal is in the head element, I'm gonna stop. Now, one of the most common questions that I get is why don't we stop at SADG? Okay, so we reached the goal, why can't we stop over here? So we reached the goal, we should stop. And the answer to that question is if we go back to this slide, notice I only stop. When do I stop? If either my queue is empty or I reach the head of the queue is the goal. And if we go back over here now and we check, yes, you have reached the goal and it is inside the queue, but it is not the element that is in the head. So I have to keep on going until I reach the head. So once my goal reaches the head, I stop. Okay, and that's the algorithm that we're teaching you and the algorithm that you have to follow. Okay, so this is how it's actually done. And if you're talking about how many nodes have been extended, so notice in the first step step I extended S. So, and when I extend S, I add 1 to it, to the extended node. Okay, and then SA I extend it again, so I add 1 more, and then I extend SB, so I add 1 more. So the number of extended node is nothing but the number of steps that you have done minus the last step where you have reached to the goal, because you do not extend this. So this is the number of steps required to reach to the goal, is the number of extended nodes. Okay, so this is basically what happens in the breadth first search. Okay, so in the breadth first search, this is actually true. It's not true for other algorithms, but for the breadth first search, it is true that the number of extended node is equal to the number of steps to reach. The next step would be the basically you have reached to the goal and you can stop. And the number of extended node, notice we start with 1, then we added SA and SB, so we add 2, so there are 3 in this queue that has been added. Then we expanded SA and we added SAB and SAD, so we add 2 more, so the 3 becomes a 5. So notice the number of children we add is 2, and the number of children added is 2. We added this is 1, so we keep adding and adding all of these, and you will find that the number of in-queued nodes, the number of nodes that have actually entered into the queue are 12. Okay, and the path that is suggested is SADG. Okay, so it's SADG, and the cost is actually 11, so we calculate the cost afterwards. But again, the breadth first search does not take in consideration the cost. Okay, so notice we did not consider the cost anywhere in this algorithm, and we're just giving you that the total cost of this path is 11. Okay, we didn't compare it with anything else. Now this 11 might be the best, might be the worst, might be something in the middle. We don't care. The breadth first search does not care about that. Okay, so that's a very important point to consider. Okay, so this is an example of a breadth first search. Okay, take care of the number of extended nodes and number of in-queued nodes, because this is something that we like to ask questions about, so that we understand that you are following up with this algorithm. Okay, here's another example. So suppose that you have something like this. Initially, this is a graph that was given to you. It's a directed graph, and in this directed graph, we want to use the BFS to reach to a goal. Okay, so we can actually turn this graph into a tree, so there is no cycle over here, so we can actually take the cycle out by repeating the G. That's a step that you can do, or you can keep that in your mind. Instead of generating the tree for the question, you can actually work on the graph, but make sure you don't make a loop when you're working in the graphs. Okay, so let's solve this problem again in step-by-step fashion. Okay, so over here I'm going to take the pen so I can actually write, and when we start we can actually go step by step, and the first thing that we add is the S. Okay, so we add the root node, which is this node. Okay, we add it to the queue, and I'm gonna say the number of in-queued node, I'm just gonna denote to it to an E, and the number of children that we add, I'm just going to denote it to C. Okay, just to have different notations. Now we have added 1 child, so I'm going to put 1 over here, and then S has not been extended yet, so this is actually 0. And then what we're going to do is we're going to generate the children of the S. Now the children of the S, how many children are there? There are 3 children, so we are going to extend 1, and then we are going to add 3 children into the number of in-queued nodes. Okay, which is represented by C over here. And this is the extended node, which is 1, so extended 1. And when we do that, we get to SA, SB, and SC. So all the three roots are now added to this. So this is SA, SB, SC. Okay, so we have extended 1 node, and we have added until now 4 nodes. Okay, then what we're going to do is we're going to take the SA and we're going to expand the SA. So we're going to delete the SA from the queue, shift the SB and SC to the front, and then expand the SA and append the children. So when we do that, what we do is we get an SB and a C, and we got SAD and SAE. So we get the D and the E, and we add them. So there are two children that we add, and sorry about that. Let me just take the eraser. I just want to do it in a format that okay, so 1 2 3 4, that's the 5, and this is the 6. Okay, so there are 6 nodes that have been enqueued, and one node that of course we have another node that has been extended. So S has been extended, SA has been extended. Okay, so there are 2 nodes. Then we take the SB and we're going to extend it in the next step. Okay, so we go to the next step and extend it, and when we extend it, we have the extended node to be 1, and notice the SB has 2 children. So the SB has 2 children. These are the 2 child of the F and the G, so the SBF and the SBG. So the SBF and the SBG have been added, so I actually added 2 more, so I have 8 actually that has been added. And this is how the enqueued nodes are going to go. And then I'm going to go and add the C. Okay, sorry, SC. I'm going to expand the SC. So when I expand the SC, I'm going to delete it from the head, shift the entire queue, and then add 2 more, which are the G and the H. Okay, and when I do that, I get 2 more nodes. Okay, so I get about 10 enqueued nodes, and then what we do is we take the head. Of course, we extended 1 more. Okay, so we have 4, and then we take the SAD, and notice the SAD, there are no children over here. So what it's going to do, it's going to delete the head, and it's not going to append anything at the end, and that is what's going to happen. Okay, so we don't add anything to the enqueued node, and it's not even extended. And we keep on doing this. So we take the SAE, there is no children for the E here also. Okay, so that's going to be deleted because we did not reach to the goal, and the goal is not in the head, although we have found the goal over here in the step 4, but since it's not in the head, we are going to keep continuing until this thing reaches the head. Okay, and that's how the algorithm works. So we take the SAE and we delete it, and then we take the SBF, so this node, and we delete it because there are no children left. Then the SBG, notice I have reached to my goal, and I stop. Okay, and this is my goal. Okay, so I reached to my goal, and the path that I have been given is the SBG. This is the path that I have been given. Okay, so this is how it's done, and you could actually see the number of extended node is basically okay. So the number of extended nodes is 7. We forgot to add the extended nodes that are going to be deleted. 5 and 6 and 7. So there are 2 nodes that being extended. So this one was extended, this one was extended, but we didn't find any children. Okay, so there were no children, so they were extended, but they have no nothing added into queue. And notice the number of enqueued nodes is 10, and we have the 10, so that's okay. And for the SB, the path that we got is an SBG, and the cost of that path, if we assume that all of them is a cost of 1, is 2. Okay, so this is basically how the algorithm is actually working. Okay, so it's pretty simple and straightforward on how this algorithm works. Let's take one more example. Okay, for the graph shown, what we want to do is to do the BFS, and we want to go from S to G again. Okay, so we're going from S to G. Okay, that's what we want to do. Okay, so let's start this again, and over here I'm going to go and do we're going to initiate our queue with S. Then we're going to take the S out and generate the children. So we'll generate, notice I'm not having a tree, but I'm going to just do it over here so that I can follow it up. I have 3 children for the A, B, and C for S, so I add them, and notice the lexical order. I add A, then B, then C. Okay, you always add in lexical order. Then we go to the next step where we have SB, and SC coming from here, so we shift them and then we expand SA. SA, when you expand it, you get SAD, and we added the SAD at the end. And then we expand the SB. So when we expand the B, notice there is SBC and SBD. So we add the SBC and SBD, and notice the lexical order again. C comes before D. And then we keep on moving. We expand the SC. When we expand the SC, we get the SCG, and we add the SCG into the Q. Now you might say that we have that G in the Q, so we should stop, and that would be the wrong step to do, because we only stop when the G is in the head. Okay, and we continue on. So we expand the SAD. So SAD will be SADG. So we put the SADG at the end of the Q, because we always append at the end of the Q. And we keep on doing this. We take the SBC, and the SBC is going to have SBCG. Okay, that's the path that's going to be added, and we add the SBCG over here, and we have in the head SBD. Okay, so SBD is in the head. Now we expand the SBD, and when we expand the SBD, we get the SBDG, and we add the SBDG at the end, and we got ourselves the SCG, and this is the goal node. So we have reached to the goal, and then we can actually stop. And if you count the number of extended nodes is 7, and if you count the number of enqueued node is nothing but 11. Okay, so this is basically how this thing is working, and it's pretty simple and easy to follow this breadth first search type of algorithm. Okay, and the path that was suggested was SCG. Now notice, let me clear the things over here. Now in this one, what is happening is the path that is suggested is SCG, and the cost of this path is a total of 8, as you can see, 7 plus 1. It's not the shortest path, because again, breadth first search does not take care of the weights. The shortest path is actually SBDG, which has a total cost of 6. Okay, so 3 plus 2 plus 1, but this is not what the breadth first search is looking for. The breadth first search ignores all the weights and then finds a path, and if it can find a path, then we are happy with that path. Okay, so this is basically what the breadth first search is doing. Okay, so let's talk about some properties of the breadth first search. So breadth first search always explores the shallowest node before the deeper nodes. Okay, and that's what one of the most important things that it does. So if you have a very large tree, and that's the reality of the problems that we have when you have big data and things and we're searching in it, the tree size might be large, very large. It might have a depth of 5 million or maybe more, and it might have billions of nodes into it. Okay, and if you want to search in that tree, then breadth first search will go level by level, and if you know beforehand what type of application do you have, then you might be lucky enough to guess what type of algorithm you should use. For example, if we have a family tree for a family that is there for like just hypothetically speaking, 1 million generations. Okay, so there is a family tree. Suppose that there is a family tree that has 1 million generations in it. Okay, so your 1 millionth grandfather is in that tree, and the tree root starts from there, and your grandfather or your grandmother, whatever, and you are basically trying in that tree to find your own sibling. Okay, now if you use a breadth first search, you are going to go level by level. So you're going to go to the millionth grandfather and take his children, and then look if your sibling is there, and then go to the next level, to the next level, to the next level, until you reach the last level. Basically, you might be the last or the second last, or you might be at the end, basically after 1 million levels, and you will find your sibling. Okay, so in that case, the breadth first search does not perform very well, because it has to explore all the levels until it reaches the final level. Okay, but it performs pretty well if you are looking for the grandson of your millionth grandfather. Okay, so if you are searching on the top of the tree, on the top, very top of the tree, breadth first search might be a very good way of doing it. But if you're searching very deep down in the tree, breadth first search is not very efficient algorithm, and that's why people have came up with other algorithms that can actually do the search. Okay. In the breadth first search, we reach a goal node with minimum number of edges from the source vertex. Okay, we do not get the best cost, but we get the minimum number of edges where the weight of the edge is not considered. So if you are looking for the shallowest node that is closest to the root node that you have, then breadth first search will give you that, and you can actually know how many levels are you beneath the root node. Okay, so it has its pros and cons, and you have to, when you're using this, decide what is the best method algorithm that you're going to be using. If the breadth first search suits your algorithm or your needs, then you can actually go ahead and do it. Now, the breadth first search is a complete algorithm. What does complete mean? It means that if the goal was in the tree that you are searching, or is it in the graph, and it's reachable, then the breadth first search will find it. It might not be the most efficient algorithm to find it, but it will find it for you. If it's there, it will find it. That's what we mean by complete. Okay, so if the goal exists, it'll find it. And the breadth first search is more suitable for searching, as I said, versus closer to the source rather than something that is very deep. Okay, and for those, we have different type of algorithms that we're going to talk about in other videos. I hope you enjoyed this video, and I hope to see you in another video pretty soon. Okay, see you. Bye bye.